of this hot stamped material. So it is a technology that is relatively well accepted and certainly proliferating throughout the stamping industries. Just have a quick picture here for you of this is the blank that is red hot. So that's the blank coming out of the furnace. The furnace would have been back to the left of this illustration, and the press and the die are probably going, oh no, here's the furnace, excuse me, drawing it sideways. There's the furnace, right? So the material came out this way out of the furnace. Here it is getting picked up after coming out of the furnace, and it's going to go this way into the stamping operation. All right, that is red hot, and that material at that temperature is above the crystallization temperature of the steel. So when you bring that material to that temperature, 950 degrees Celsius, 850 degrees Celsius, that material is a superheated liquid, right? It's or excuse me, a supercooled liquid. That material is solid enough to have form and shape and to be picked up, but its crystal structure is still relatively undefined. And it's not until that material starts to cool that we see the individual crystals or grains of the material set up in whatever the microstructure of that material is. So this material is highly pliable, highly deformable, but how it still has not yet decided what kind of material it's going to be once it cools to room temperature, because that depends on how we cool it. So when we take this idea of the direct hot forming process, we take that boron steel, we take it from room temperature to 950 degrees C in the furnace, and that heats that material up to its austenitic microstructure, right? That's the relatively amorphous, not fully formed grains or crystal structure microstructure. We form it inside of the die, and you'll notice I have all these little blue circles inside my illustration. Each one of those represents a liquid-filled cooling channel. Right, so this die is going to be piped, and it's going to have fluids passing through that die trying to maintain a particular temperature. And that way, when we close the die on the material is getting deformed and the material is quenching in the meantime. So normally what will happen is you put the blank in, it takes 1 second, maybe 1.5 seconds to close the die, and then the die is going to stay closed, maybe dwelling at the bottom for, I don't know, 3, 5, maybe even 6 seconds, cooling and quenching at the bottom of the stroke. And as that's happening, the material's microstructure is going from this 950 degree austenitic microstructure possibly towards martensite or bainite or ferrite microstructure, and achieving certain yield strength and tensile strength characteristics. Some of the things that we're doing with these hot forming and hot stamping dies is that you can take the die and you can actually, in this illustration you'll see that I have one area that is shaded blue and I have another area shaded red. And what you can do is you can have maybe one area of the tool is being held at 400, 450 degrees Celsius, and the other tool is being held at 80 degrees Celsius. When you take the big superheated blank and you close it inside of a die that has these two different heating zones, what you're going to end up with is a different rate of cooling in the top half of that panel compared to the bottom half of that panel. And by changing the quenching characteristics, we get different material characteristics as we form this panel. So this is something that people might use the term tailor tempered. So tailored, like the guy who fixes your pants or your shirts, tailored tempering allows us to very specifically control the material parameters, the material properties of the finished product by controlling the temperature at which this material quenches. So if I quench just the top part of this B pillar at 80 degrees C and I held the lower part of the die at 400 degrees Celsius, what will happen is that the lower part of the die would B-pillar would not form this martensite. It would form more ferrite, more bainite in its microstructure, and therefore it would not have the super strong 1000 megapascal finished yield strength. It would finish up in strength more like what the material's original strength was when we received it from the steel mill. This material at the top, where we're quenching it to that 80 degrees C using this very cool tool, that's going to form a higher degree of this martensite, and that top of the B-pillar would presumably be all at this martensitic microstructure and achieving that 1000 megapascal yield strength. So here's an illustration of a part that was produced specifically for a simulation benchmark study by an organization called Numisheet. And you can see here, there's that blank. That blank's still red hot. And you'll notice that it's touching at the top of that of the die, right about midway through that B-pillar. And it's also resting a little bit here at the bottom. And as soon as that die starts making contact with the sheet metal, the die is going to start acting like a heat sink for the material, drawing out some of that heat, causing it to cool or quench maybe a little bit earlier than was planned. And therefore, when we talk about this hot stamping, it's really we've really seen that this idea of hot stamping, hot forming is something that's going to be very reliant on our ability to engineer and mathematically simulate these forming operations in order to assure that we get the product characteristics that we finally wanted. Because it is possible that this early contact in these different areas of the blank, or even where we're holding it with whatever robot or automations loading that blank in, any initial contact could cause the material to cool at a different rate and not quite get the material properties that we were aiming for. Here's another illustration. These are photos of actual dies that were provided by Braun Cartech, but you can see here, this shows very clearly how that heating channel is distributed inside of our casting. Right? So inside our casting, this is a punch for what could be one of those tunnels from the front of the vehicle for a rear-wheel drive vehicle. This is the tunnel, and you can see here that the die post is pretty much a solid tool, except for this pattern of cooling channels that had to be designed and piped through the tool in order to help maintain that temperature. Here's a CAD illustration showing how we might have to design our tools a little bit differently in order to assure that we have the individual heating channels, and maybe if we're heating one part of the die differently than the other, it creates a very interesting design challenge of how do we make sure that one half of the die perhaps is held at one temperature while the other half of the die is held at another temperature. Here's an example of this is a photo of a part in that indirect hot forming. You can see that this part is coming out of the furnace red hot, and it already has some product shape applied to it. So in this case, this was indirect hot forming. They did some room temperature deformation of the part at ambient or room temperature. Then it went through the furnace to get heated up to the appropriate temperature, and then hot formed and additionally quenched and cooled in that environment. And that gives you perhaps the ability to form even more sophisticated, more complicated shapes than we would have achieved if we just did it in one hit. So the thing that happens is that as we start looking at this type of deformation, it adds a new layer, a new level of complexity to our metal forming operations. Right? We are going to end up having to understand that temperature is now an additional process parameter, one that we'll have to plan for and try to control and try to make sure that we can predict how the temperature is going to affect this forming operation and the product performance. So that means that we have to have material characteristics mapped out for that part at different temperatures that we might see throughout the forming operation. So that means a much more complicated methodology of testing our material as it comes in before it comes into our mill, and the ability to predict how does that material behave stress and strain wise at 800 degrees Celsius compared to 500 degrees Celsius. We also have to know not only how do the different temperatures behave, but material also has different strain rates. The faster it stretches compared to being stretched slowly, we do see different characteristics between the stress of the material and its strain, and therefore another complexity of our forming operation in order to mathematically model it. Here's some discussion on this idea of tailored tempering. I mentioned it briefly before. Tailored tempering, perhaps for this particular B-pillar, we wanted tailored tempered because at the bottom portion of the B-pillar compared to the top, we want different overall tensile and yield strengths in order to get different characteristics of the finished part. So in this case, the B-pillar, they quenched the B-pillar at the top. That's going to form a lot of that martensite microstructure. That's going to be the strongest, highest strength material that this B-pillar is ever going to see. Then there's going to be a little bit of a transition zone to the material that is allowed to cool or quench slowly. So the die at the bottom portion of this B-pillar is being maintained at around 400 degrees Celsius. And by holding that die warmer during the forming operation, we ensure that its microstructure is different than the top half, which is being cooled to 80 degrees Celsius. And that means that we're going to have a much higher strength material at the end of the forming operation for this top part of the B-pillar, and then a much lower overall yield strength and tensile strength of the lower portion of the B-pillar. And that was engineered for and designed in order to give a certain product performance for that B-pillar that was selected by the structural or product engineer. So any of that material that is cooled very quickly forms martensite. The martensite grain structure is a very small grain. Those grains are having a different crystal structure that lends them a very high strength characteristic. If you cool the material a little bit slower, now you don't have 100% martensite. Maybe you end up with 99% martensite, 1% bainite, and that's going to give you a different characteristic and finished part. And then if you cool this at a much slower cooling rate by holding that die a little bit warmer, then you're going to have maybe only 90% martensite and 10% bainite. And that material is going to end up being, as far as its strength, closer to that mill spec original strength of the material, as opposed to being that tempered, highly quenched strength that we get when we were talking about the martensite. And you can see in simulation what we want to validate for our product engineers. We want to prove to them that the area that they designed to be 100% martensite did in fact achieve all of the strength that we were targeting. So the top part of this little pillar reinforcement I'm showing here has 100% martensite in this portion of the B pillar, or this is an A pillar, excuse me. But you can also notice that there's lower percentages of martensite. In this purple area, we're seeing martensite levels as low as 10%. So that material is going to be more like the original strength of the mild steel, of the not the mild steel, but of the steel directly from the stamping mill, the coil mill. It's not going to have that value-added quenching characteristic of being increased in strength. But you'll also notice a manufacturing-induced difference that we recognize, that perhaps in these two areas I just circled, maybe those two areas were areas where had early contact with the die during the forming operation. Those were, in fact, in this simulation that I ran, I had spring-loaded pads to support the blank prior to closing the tool in this operation. And where the blank was resting on this tool, it was acting as a heat sink, and it was drawing that heat out of the tool at a faster rate than did the rest of this A-pillar, where we have some ability to put cooling channels or heating channels through the die in order to maintain the 400 degrees Celsius temperature. So the rest of this A-pillar was being maintained at 400 degrees C, except for the little spring-loaded pads that were controlling this blank's orientation during the loading. And what happened is that we ended up with areas having more martensite than perhaps people might have planned for. And what that means is that these two areas are going to be stronger than the areas adjacent to them. And that could lead to maybe assembly problems, or that could lead to a difference in product performance that they didn't perhaps foresee or plan for. And you can see we also will not only measure and try to predict that microstructure, but also show what is the hardness of the material, right? The strength and the stress of the material relevant and being measured in terms of Vickers hardness. What is the strength of the material in these areas? And again, where I see this orange coloring, those are materials that, because of their martensite purity, their martensite content, are very high in the hardness scale. And these areas where I had my pads were a little bit lower in the overall hardness scale, but still significantly harder and stronger than the areas next to them, which are in these blue or aquamarine shades. So it's very important to validate our assumptions in the manufacturing and product design process. And the way that we're doing that these days is through metal forming simulation. And that's about what I think we can squeeze into our conversation today.